All right, now I mentioned that Io is actually not in a synchronous tidally locked orbit, which is surprising because at Io's distance from Jupiter, comparable to the moon's distance from the Earth, the Earth's gravitational tidal effect is enough to make the moon be tidally locked. So how can Io somehow manage to not be tidally locked when it's hovering so close to this giant planet with 300 times Earth's mass? Well, okay, we'll answer that in a moment, but just to look at some unique phenomenon on Io, it actually has active volcanoes. We have literally seen volcanoes in action when we fly by with spacecraft looking at Io. We don't see that anywhere else in the solar system. We don't even see that directly on Venus because Venus is shrouded by an atmosphere. Io you can see right down to the surface, and you actually can see volcanoes in action on Io. So we think that the heating that's driving the volcanic activity on Io actually is due to the tidal force of Jupiter. And this brings us back to this question of, well, why isn't Io in a synchronous orbit? If it were synchronous, it would have the same phase facing Jupiter, and it wouldn't be heated like crazy anymore because it would keep the same phase toward Jupiter, so you wouldn't have the tidal bulge moving around through the rock, and that's what actually causes the heating. Well, we think it's the gravitational influence of the next moon out, Europa, that is tugging sufficiently hard on Io to cause it to be in a slightly elliptical orbit. And remember that elliptical orbits can't be perfectly tidally locked. We actually saw this already in the case of Mercury. Because Mercury is in an elliptical orbit, it actually can't be tidally locked. Because the problem is that as you move through the elliptical orbit, your speed, remember, is changing. It's faster when you're close to the Sun or close to Jupiter. You have faster motion. But the spin is just constant. It's spinning like a top. So Io is spinning like a top, and therefore its rate of spin is the same. So if you try to match the spin rate with the orbital rate at the maximum distance, then it won't be equal rates at the closest distance. This is exactly what we saw in the case of Mercury. So, okay, so the bottom line is that, ironically, even though Io is closest to Jupiter, it actually is the only one that's not in a tidally locked orbit, and the reason is because of the perturbing influence of Europa. And with Io not tidally locked, it means that Io is spinning a little bit relative to Jupiter, and then you have this tidal bulge effect moving through the rock on Io as it spins. Because remember, the tidal bulges are going to point towards Jupiter and away from Jupiter. But if Io spins, then different parts of Io are moving into that tidal bulge region, and therefore the rock is expanding and getting crunched up. And that's what actually leading to the heat that drives the volcanoes. All right, so moving out to Europa, we're already starting to see an icy crust, remember. And when we look at Europa with passing spacecraft, we see a very icy fractured surface, completely unlike what we see in the case of Io, for instance. Just a lot of cracks in an icy surface that seem to indicate a long period of bombardment, as well as maybe some icy sort of tectonic activity we don't really understand very well. Lots of bizarre details like fracture lines that are perpendicular to other fracture lines, which could be the result of, again, some kind of icy tectonic process occurring, or possibly something to do with collisions. And we also see the classic sort of thing that we see on Earth when there's a rock embedded in a snowbank. Rocks tend to be darker colored so they absorb sunlight, and then they melt the surrounding ice. And you see that exact thing happening also in the case of Europa's surface, with rocks that were probably deposited in a meteor or asteroid impact. But again, notice the crazy pattern of crisscross lines here. It's very difficult to explain that in detail, really. It actually looks a little like, sort of instead of the Wright brothers, the little green Guy brothers, launching their some sort of craft there. Okay, so moving a little farther out now, we're out to the third Galilean moon. Working our way out from Jupiter. This is Ganymede. Again, it's actually an icy surface. It's more icy than what we just saw in Europa. And now we're out to almost around 1 million kilometers from Jupiter. So it's far enough out that it again was protected from completely melting. But we see large dark regions, which we think are due to radiation darkening, which tends to affect ices by darkening them. But you can still ask, well, why is this region darker than some of these other regions? It's obviously not uniform, which probably indicates the non-uniformity of the composition of the surface. Again, another shot of Ganymede, and another shot of Ganymede. This was a lot of aliens racing here, you can see. Now, I left Io sort of almost till the end here. Now, Io has just got this totally bizarre, incredible surface. The bottom line reason that this looks so bizarre is because it's not tidally locked. Because it's got a little bit of spin relative to Jupiter. Jupiter's massive tidal effect is just eating the guts of Io all the way through the whole body. And that's actually keeping it molten. There's actually a lot of molten sulfurous material. And if we make a time-lapse set of images here, well, this right here is sort of a sulfurous plume of material coming out of an active volcano on Io. And here's another shot. This is actually, I think another Cassini shot. As Cassini went by Io, you can actually see a plume, a geyser-like plume on the edge of the planet. And again, we see over short periods of time, pretty dramatic changes on the surface. For example, if you compare these two images, you can actually see that this plume has moved farther out here, this plume of sulfurous material. So it's really quite an active body, all driven by this heat of the tidal effect. This looks downright painful right here. There's a really nasty gash there. Lots of sulfur on the surface. Sulfur collectors, good place. Good to go. Now, this particular shot is a full sort of projection of the entire surface of Io unwrapped and laid flat. And this came out around the same time that Pizza Hut was having a special on a certain type of pizza, around the time of the Super Bowl some year, I asked. But it was called the Bigfoot Pizza. And I saw the Bigfoot Pizza, of course, immediately my mind leaped to this image of Io. And it does raise actually a serious scientific question about whether or not we could actually be seeing stuff pressed on Io. Nobody's actually seriously proposed it. You never really know. All right, now this one remaining body, which we hadn't talked about, this is the final of the Galilean moons, the outermost one. Again, passed roughly 1 million kilometers out, Callisto. So again, you're seeing the radiation darkening of an icy surface. It's interesting to note that this is more uniform than what we saw on Ganymede. So this is a body which seems quite homogeneous. The properties are probably pretty consistent over the surface. And that's why the radiation darkening has produced a pretty consistent pattern, unlike what you saw on Ganymede, which might have had some sorts of reprocessing occurring during its semi-molten period. But Callisto never was semi-molten at all. When I showed you the interior, remember, it was homogeneous rock and ice. This is basically primordial, and the surface is quite uniform for that reason. And again, just another Voyager shot. Now, of course, these bodies have definitely been subject to multiple impacts, so that's something that would have affected the surfaces of any of these bodies. The icy surface is revealed by the form of some of these craters, which again look kind of like regions where we've had impact on ice. All right, so again, to summarize, we see more ice and less differentiation of the moons themselves as we move out away from Jupiter. And this is pretty clearly explained by the fact that we have less heating from the primordial Jupiter as we move out away from Jupiter. Now remember, today's Jupiter isn't hot enough to directly heat any of these moons. So the reason that Io is hot has nothing to do with Jupiter's own temperature. That's just because of the tidal effect of Jupiter. And Jupiter actually does have a ring, but it's sort of not really winning the bragging rights contest with Saturn at this point in time. Saturn definitely has the body of rings. But as we'll see when we talk about Saturn, the ring systems themselves seem to be kind of transient phenomenon that may only last for hundreds of thousands of years. It's a very short amount of time when you're talking about astronomy or geology. So it is possible that as we see how these rings develop, Jupiter could, in 100,000 years, actually be the dominant ring planet in the solar system instead of Saturn. Speaking of Saturn, move on to the next chapter, try to wrap up as much as we can today, chapter 10. All right, now, obviously a pretty cool photo of Saturn. You can see the rings, and you can also see some structure in the rings. Now, how can we tell that this shot was not taken from anywhere near the Earth? pretty obvious reasons that we can tell that this was not taken from anywhere near Earth. I talked about that. Yes. Exactly. Yeah, we're actually seeing the shadow of Saturn on its own ring there. And remember that the sun is in the direction of the bright side of Saturn, right? But at this scale, Earth and the sun would be miles away in that direction. So from the Earth, we're only ever going to see the bright side of Saturn. We're never going to see the far side with the shadow and the rings and all that. Okay, so again, moving continually through the outer solar system. Now we've passed Jupiter. We're moving out to Saturn. 9.5 astronomical units out, almost 10 times farther out from the sun than the Earth is. So we view this as our sort of continuing to penetrate farther into the outer solar system. And temperatures are going to continue to drop dramatically. Because we are seeing about a doubling of the distance going from Jupiter to Saturn. The solar radiation drops off by 1 over the distance squared. Okay, so if we double the distance going from Jupiter to Saturn, it means we're seeing about 1/4 the amount of solar heating at Saturn than we were seeing at Jupiter. And Jupiter already was mighty cold. Remember, with icy clouds and things like that that are features we don't see on Earth. So we can expect to see a continuation of that trend on Saturn. It's a giant planet, 9 times the size of Earth versus 11. So it's comparable to the size of Jupiter. Actually, it's much less massive, though. 95 times the mass of the Earth. A giant planet, the second most massive planet in the solar system, but less than 1/3 the mass of Jupiter. So when we consider the fact that the radii or diameters are pretty comparable, but the mass is way down, we could sort of expect that this final column here, the density of Saturn, is going to be lower than Jupiter. And it is. It's only about half the density of Jupiter. Now we're down to only 0.69 grams per cubic centimeter. That's actually less than the density of liquid water. And it's the lowest density of any of the planets in the solar system. All right, so just to contrast these properties with earthly units, so here's this table. Looking at the distance relative to the Earth, of course, is 9.5, that's astronomical units. The density is down to only about 10% of Earth's density, and the mass is still, of course, very, very high because this is a giant planet. Hubble photos of Saturn, and very good ground-based photos, reveal that the ring structure is pretty complex. You don't necessarily realize this when you look at Saturn, typical photos of Saturn. You know it has a very nice ring, and through a small telescope you can see the ring of Saturn very clearly, but you don't really see these features unless you go to a larger telescope. You maybe see this Cassini division in a small telescope, but the point here is that we're seeing a couple of different types of effects here. We're seeing some structure in the rings. We also see that the rings are in a very tight plane. They're not haphazard at different angles. They're in a single tight plane. And we also see cloud bands on Saturn. But if you harken back to what we just discussed in Jupiter in the last lecture, this is much more muted kind of pattern of colors than what we saw in the case of Jupiter. We saw reds and blues, a little bit of yellowish color in the case of Jupiter. But here, it's much more limited palette of color. So we like to sort of look into why that might be the case.